and 9 and 10 and 11. So that's in CSP next week. Schedule change, but I wrote it WebEx schedule change. We had a Monday quiz. I moved that to Tuesday. It's next week, so it's a Tuesday theme for this unit. Apparently, big things happen on Tuesdays. What? I changed quiz through. Quiz. Oh, crap. Rats. Thank you. Wait, I can fix that. Well, quiz 2 is on a Tuesday, but it's on a different Tuesday. This is supposed to be, I'm correcting it now, quiz 3. There we go. Quiz 3 is changed. I think quiz 2 is always on Tuesday. If you look at, I WebExed out the schedule. There it is. Well, that's still super chunky. I'm just in WebEx looking at it. Yeah, we've always had a quiz tomorrow. The one the following week I moved. Okay. All right, so our essential question, which you can find in Blackboard, you can also find it on our whiteboard. It's kind of funny, in Blackboard and on the whiteboard. Maybe that's funny to start with. What vocabulary are we going to use to connect the accumulation of the area to the function to create? Okay, so kind of a big day. So as you went through the notes, basically what we noticed is that if we accumulate a region, it becomes the difference in the function values over that interval that you calculate the area of. And we are going to call that the fundamental theorem of calculus part 1. We call it the evaluation part, as opposed to the derivative part that we learned last week. This is where we are evaluating that interval. So I haven't said it in a while, but remember that intervals are going to change the value, right, over a certain domain. That's why we have a lower and an upper limit on our definite integrals. And so that change in that function value is that function that results as a result of accumulating that function, accumulating that area. So, and then we went through some examples here, and we introduced this new word, antiderivative, which is meant to be somewhat intuitive, because basically we know that we have the derivative and the integrand, and so we're trying to figure out that function we had originally before we differentiated. So a fundamental theorem of calculus can be used to evaluate a definite integral as long as we can find the antiderivative. Okay, so the idea is if we can find the antiderivative, we no longer have to do an area calculation. We can just look at that function that's created. Antiderivatives can be described many ways. We went through a couple of examples in the notes. Graphically, I went through a table example, we went through a symbolic representation. Definite integrals can be calculated on your calculator. So remember we had a math 8 key for calculating derivatives and evaluating them at a certain location, because that was the slope of the tangent line, so that was at one point. Well, we have a math 9 key, just right below our math 8 key, where we can evaluate a definite integral. So our calculators actually can do this area calculation for us. And so we're going to do that today in class. So it's a powerful thing to be able to do. Keep in mind that there's a lot we expect using the calculator, so it doesn't take the place of knowing how to find the antiderivative. That's a big component of second semester, being able to do this without a calculator. So questions so far? No questions so far. Sorry, I'm just doing a quick check here. I do think I started. Yeah, I did start recording. Okay. Awesome. Okay. So moving on to that. So some examples. This is at the bottom of your notes. I kind of stopped the notes earlier. I was trying to go through a couple of things face to face. Some examples of g prime of x. What would the definite integral represent? So the idea is I'm giving you the derivatives here. So the rate at which a person makes friends and people per day. If I integrated that, what would it give me? If I integrated this rate, what would I end up with over an interval of, in this case, days? Yeah, exactly. Right? It's an accumulation function. I'm going to make 2 friends this day and 3 friends that day and 2 friends that day and 6 friends that day. I should be able to accumulate that over the number of days that I've been making friends and figure out how many friends I have. Right? So let's just kind of pretend this is our rate of change. Make that many friends one day and that many friends the next day, and so on and so forth. If I accumulate that over my number of days, then I know my rate is people per day. I'm measuring over days. I should be able to take those. We do this a lot in physics. I think it's probably the most common way of thinking about doing this sort of thing. I take the units, I can multiply the units together because they represent the width and the height of any Riemann sum. And the time factor cancels out with the number of people, number of friends I make. So good. So a couple of key things. First of all, make sure your intervals are represented by the same unit. I have days and days. You don't want days and minutes or something like that. And then if your units of time match, you can get rid of those. They're going to cancel in the accumulation sort of environment. So this next one, rate at which the children consume jelly beans in pounds per minute. So I'm sitting here with a stopwatch, maybe a wristwatch, and I watch some kids eating jelly beans. Mildly amusing. Huh. Yeah, how many pounds of jelly beans those kids consume, right? So I can represent that with the same function. I don't have to really be thinking about the function. Pounds per minute. I watch them for 10 minutes, let's say. I should get the total number of pounds. In other words, the minutes cancel. Total number of pounds of jelly beans that they ate over that time. So far, so good. So I'm kind of extending. No, I can't say that yet. They haven't gotten to that question yet. Sorry, my bad. We haven't looked at that question yet. So the rate at which pollutants escape from the smokestack in tons per month. So if I look at that for say 3 months, what am I going to find? Tons of pollutants, right? What has left that smokestack cumulatively? In other words, how it's accumulated. Well, I'm going to be boring and stick with the same looking function, right? So tons per month over the number of months we look at this, we're going to get our tons of pollutants. Okay, that's the whole idea of accumulation, right? We're watching something accumulate. We can also watch something kind of like deteriorate, right? Go away. So it just, we just take the whole function and stick it in the whole quadrant so that it has a negative function value, and then we can make all those values negative. Okay, so this sort of we call it dimensional analysis or unit analysis. That is what they're getting at in 1B. So this is a calculator question, so you should have your graphing calculators out. Your handheld works better than your iPad, and plus you can't use your iPad on at least not that we know of so far. So So definitely get used to using your handheld on these things. So we have a temperature of water in a tub, and it's modeled by a strictly increasing twice differentiable function W. So strictly increasing, which means it doesn't do what? Doesn't decrease, doesn't stay the same. Twice differentiable, how does that help us? That means what exists? Hear me? Okay, every point exists. What can I do to W? I can find not just the first derivative, but the second derivative, right? Okay, so that means I can do all of the things that I've learned in calculus, which is good because then we don't have to make any special circumstances here. Okay, so W is measured in Fahrenheit, T is measured in minutes. At time T equals 0, the temperature of the water is 55 degrees. So they're giving you a starting point. And with the fundamental theorem of calculus, that's really important. Okay, that's our first evaluation point. The water is heated for 30 minutes. Notice that our table only goes out to 20 minutes. Interesting. Beginning at time T equals 0. Values of W are selected at times T for the first 20 minutes. So there's my temperature as it's fluctuating in the first 20 minutes. Use the data to evaluate the integral from 0 to 20 of W prime T dt using correct units, interpret the meaning of the context of this problem. So this is where the units come in. When they say using correct units, all they want you to do is they want you to do the calculus, and then they want you to put the right units out there. Okay, that's what they mean by interpret the meaning of that using the correct unit. Okay, do we know W prime? No. Do we know W? We do? We know some values. Okay, so the point I'm getting at is that if you don't know W prime, so you can't try to integrate anything, a function, you can't try to find the antiderivative, we have to rely on the fundamental theorem of calculus part 1. In other words, we have to realize that this notation here, integrating W prime, just means that I want you to take the difference of my values in the table. Okay? So we talked about tables being really limiting, right? There's only a few things we can do with tables. We can calculate slope from a table, but it's only an average slope. It's not calculus based. I can have you do difference in values from the table. And then the last thing is I can have you do a Riemann sum from the table. Those are the only 3 things you can do with a table. There's got to be one of those 3 things I'm asking you. Okay, if I give you a table. So what is the integral from 0 to 20 of W prime T dt? It is. It's the W of 20, my final temperature minus my initial temperature. So it's 16 degrees Fahrenheit. This wasn't supposed to pop up right away. Sorry about that. Okay. So you putting the degrees Fahrenheit on the end is using the correct units to interpret the meaning. Okay. So temperatures increased by 16 degrees Fahrenheit. Remember that evaluating reference integral is change in a quantity. What changed the temperature? What did it do? It got hotter by 16 degrees Fahrenheit. Is that so good? Okay. So part D, notice I'm cherry picking here. I'm not giving you all the parts. Says for 20 to 25, minutes. The function W that models the water temperature has the first derivative given by that awfully complicated looking thing. Okay, so remember I said, it's interesting that they said for the first 30 minutes, but they only gave us a table out to the first 20 minutes. Okay, so you knew some calculus might be happening there. It says based on the model, what is the temperature of the water at time t equals 25? Okay. So this rate of change of temperature is only valid from 20 to 25 minutes. That makes sense? You can't use this rate of change before 20 minutes or after 25 minutes. Okay, so we need to integrate this to figure out how our temperature has changed. We can do that right on our calculator. So what we're going to do is we are going to do a math 9. So find your math key. Okay. Math. And then 9. Here's our math A key, right? That's our end derivative key. Our math 9 is our integration key. It's function integration. Okay, so math 9. And I'm going to type in exactly what I see. My lower bound is 20. I'm going to arrow up to my upper bound. It's 25. And I'm going to put in my function. Now, on the question, the function is written in terms of t. We don't have a t variable on our calculator, so we just use variable x. All right, our typical variable key. So here's the function 0.4. So 0.4 times the square root. So I'm going to grab my square root, second square root. X is my variable key, so that variable key is right next to alpha. Keep going with me second. So there's 0.4 square root x. And I'm going to hit my right arrow because I need to get out from underneath that radical. And then I need to do a cosine. Come down here, grab my cosine. Calculator puts in a bracket for me. 0.06. Get that 0.6 t. So grab my variable x. Okay. It looks like I need to put a bracket in there because that bracket next to it is the beginning ending bracket. So I'm going to stick a bracket in there. A parentheses, whatever you use for that. Then I'm going to arrow to the right and make sure that the differential has the variable x so that the calculator knows which variable to differentiate. Okay, so now I could press enter, but I want to be sure I have a few things set up first. What do I need set up first? It's important to be out. For me? Yep, exactly. How come? Well, and not just graph. What do we use radian mode with? A tree. Yeah, a tree, right? Once we see a trig function, we be sure we're in radian mode. I say this because if you're taking physics at all, right, you're living in the probability world, so be careful that you are in the right mode. Okay, so it looks like I'm in the right mode, so I'm going to hit second quit on there. Now I can just hit it. And I get 2.04315 and some other decimal points, or some other digits. Okay, how many decimal points do we keep? 3. Okay, so 2.043. If you want to keep 4 or 5 decimal places, that's fine. Just round correctly. Okay, what does that represent? Yeah, how much the temperature changed from 20 to 25 minutes? So does that answer the question? No, it doesn't answer the question. There's my question. But it helps. We need that information, right? But we want this information. Right, this is where the fundamental theorem of calculus part 1 comes in again. We just calculated this on our calculator. That's not what they're asking. They're asking for the temperature at time t is 25. They're asking for this. So then it becomes just solving this, right? If I want to find this, I'm taking this to the other side, so I'm adding it to both sides. So that means I'm starting at what temperature? My temperature at 20 minutes. 71. And then I'm going to add this to it. So I'm going to be somewhere near 73, 73.043. So notice when I calculated it, I kept an extra couple decimal places just because I did. This is the answer that they grade. So definitely at least three decimal places in. You could have more applications. All right. Okay. Okay. So what is the vocabulary? So we need to settle on vocabulary. That's kind of the point of this right now, because we have a lot of vocabulary floating around. Okay, we're going to start calling the accumulation function. We're going to start calling it the definite integral. Okay, and we're going to start calling the function it creates the antiderivative. We're going to settle on those two. Accumulation function is going to go kind of by the wayside. The function it creates is going to go by the wayside. We have definite integral and the antiderivative. We're going to settle on that terminology. Okay, you've got, oh, I didn't even finish the numbering. You've got, it is 6. So you've got 6 real quick questions in College Board, and then 2 con for tonight. And you got about 15 minutes to work on the topic questions. Probably won't take more than 15 minutes for this topic question time, because it's a lot of fundamental theorem calculus. It's either using the calculator or just subtracting 2 values. All right, people at home, I am still here. I'm just stopping the recording and muting my